sky never lied and brought me to the dark. One by one into the fire.
Looking into our universe opens up dimensions way beyond the orders of magnitude that our minds can imagine. At the same time, there is a world that is just as difficult for us to grasp. Venturing into the structures of the smallest particles of matter exceeds the scale to which we are accustomed. In both areas, only mathematical and theoretical models can help. To be able to explain the world at its very largest scale, the universe, we need to know its most elementary building blocks, and vice versa, macrocosm and microcosm, as contrast and unity.
Microcosm and macrocosm. Together, they determine the properties of our universe, although they are subject to vastly different properties. For example, in the macrocosm there are black holes with singularities, whereas a microcosm with singularities could not exist at all. On the other hand, in the microcosm there are elementary particles which can have contradictory properties simultaneously. For example, an electron can exist here and there at the same time. The elementary particles essentially determine what happens in the universe. Without quantum physics, we cannot understand what happened during the Big Bang or in stars. In other words, we can only understand the universe if we understand the elementary particles.
Our universe is 13.8 billion years old. A look into the depths of space is a look into the past, and a glimpse into an incomprehensible infinity. The night sky with its stars is the part of our universe that is visible to the unaided eye, filled with cosmic structures of indescribable size. And yet we can only see a tiny section of it, a small part of the macrocosm, the full extent of which is beyond our imagination. But the universe, the world as a whole, is ultimately determined by the miniature world of particles. And the origin of the universe and everything in it lies in a tiny point, the Big Bang.
Now, this is a volume where we no longer need astronomy. Instead, processes are taking place in the smallest volumes, which are quantum processes. And that means the universe that we see now, with its beauties like a tree that I look at outside, with its stars, with the sun, was in principle a quantum universe. From today's perspective, this was boring for people who look at the beauty of trees, but it was enormously exciting for particle physicists because the entire field of particle physics opened up before them. And that was life shortly after the Big Bang, so to speak. Pure quantum physics.
The world of quanta, the world of the very smallest particles, is a strange world that seems to contradict our everyday experiences. But these building blocks in the smallest dimensions determine our universe and therefore our lives. They do not obey the laws of classical physics. The world of quanta is a cornerstone of modern physics, and yet it seems to be completely different from the reality we live in. Quantum physics determines our cosmos from a hidden world, and it is full of mysteries.
Explaining quantum physics to a normal person, by which I mean a non-physicist, is incredibly difficult because even physicists have a problem understanding quantum physics and its implications. There's the famous statement by Richard Feynman, who once said that anyone who claims to have understood quantum physics has not understood it. And there is something to this statement, because we are ultimately leaving the world of the observable. We can no longer imagine the consequences or the facts of quantum physics with our brains.
As a young physicist, Nobel Prize winner Richard Feynman was involved in the Manhattan Project, the construction of the first atomic bomb. The bomb was based on the revolutionary new quantum theory. The most horrific weapon ever used against humans was one of the early technological applications of quantum physics. Feynman famously lectured on quantum mechanics in the 1960s and spent a lifetime trying to understand it. But you can only get used to it, the physicist admitted.
Of course, it's a process of getting used to it. And naturally, there's also the question of what is paradoxical. The quantum world works differently than the world we live in. We're not used to quantum mechanics. If you deal with quantum processes more often and go through the computations more often, then at some point you understand them. And then you get used to how it happens and what happens.
In the microcosm of the quantum world, many things work much differently from the cosmos we know. Nevertheless, the basis for the world at large lies there.
For example, if I know that wind, that is, both moving air as well as the temperature, can be attributed to the movement of particles, then I have understood something about air. Then I have understood something about the wind. And in this sense, we understand quantum mechanics. So we know which principles we can attribute the behavior of atoms to, which principles we can use to calculate electrons. And we can calculate exactly, to many decimal places, how an atom behaves, or how an electron behaves under certain conditions. In this sense, we understand quantum mechanics. There are uncertainties in quantum mechanics that we don't yet understand, but essentially we can trace many things about atoms, for example, every atom in the periodic table of elements, back to a few basic principles of how quantum mechanics works. And in that sense, we have understood it.
In the world of atoms and elementary particles, the concept of probability prevails. Particles with certain probabilities can be in two places at the same time. This contradicts our intuition. But quantum theory can predict these probabilities exactly, and they are always confirmed experimentally. This proves that quantum theory must be correct. But that doesn't change the fact that we don't understand it.
Quantum physics is extremely paradoxical because quantum physics tells us, for example, that if you have what a physicist calls a quantum mechanical system, then this quantum mechanical system can be in different states. And quantum physics tells us that the system is in these states, and in fact in all states simultaneously, as long as you're not looking. The moment you look, you force the system to assume a state. For example, if you want to measure the energy state of an electron in a hydrogen atom, then anything is possible at first. But the moment you measure and get a value displayed, you have created reality, so to speak.
Our galaxy consists of hundreds of billions of stars. The universe visible to us consists of an estimated 100 billion galaxies. Including all the energies present in the universe, that is only 5% of the form of matter known to us. The large remainder is made up of around 27% dark matter and around 68% dark energy. The Big Bang is the origin of our existence. In a single moment, all the particles of the universe were created, the building blocks from which everything we know is formed. The result of probability, or perhaps a coincidence.
Protons and neutrons were created from building blocks such as quarks, and nuclei such as helium were created from protons and neutrons. That all happened in the first 3 minutes. And our entire universe, which developed afterwards, is based on the products of the first 3 minutes. If the laws of nature had been slightly different in the first 3 minutes, our universe would look completely different today.
Our cosmos is based on the processes that took place in the first moments after the Big Bang. a world of quantum physics. It seems difficult to comprehend, but that is no reason to doubt it. Our understanding of the world as a whole is the result of how we experience this world. So we should not be surprised if things in the microcosm and macrocosm that we cannot experience elude our understanding. Black holes weighing millions of solar masses in which time comes to a standstill also elude our understanding.
The quantum world can be pretty crazy. There's a beautiful example, Schrödinger's cat. Here in this box is the cat. Before I tell you anything about it, you need to know about the so-called superposition principle in quantum physics. Let's assume that the cat is an elementary particle. An elementary particle can usually be in different states. Suppose green or red state. Quantum physics then says that there's also a green state wave and a red state wave. And as long as we don't know which state the elementary particle is in, we have to assume that both waves exist simultaneously. This is called the superposition principle. So, now we get back to the cat. Let's assume that the cat is an elementary particle. We have a toxic source next to it, and we don't know when it will be unleashed. That's why we don't know if and when the cat is dead or alive. It exists in both states. Quantum physics says that I only know whether it's dead or alive when I look at it. I'll have a look now.
Schrödinger's cat is probably the most famous animal in the care of physicists. The example raises questions about the nature of reality and human perception. A world full of possibilities until we measure them. The cat in the box has become part of pop culture.
As a physicist, you're often asked about Schrödinger's cat, and you always find it difficult to explain.
The thought experiment was devised by physicist Erwin Schrödinger in 1935. As far as we know, Erwin Schrödinger had nothing against cats. The physicist only wanted to point out paradoxical phenomena within quantum theory. Almost 10 years earlier, in 1926, he formulated the basic equation of quantum mechanics, the Schrödinger equation, named after him. According to this equation, every particle in the microcosm has many possible states of existence at any given time, each with a different probability of becoming real.
In quantum physics, you can only speak of probabilities. I know the probability with which a system that was somehow in this state at time zero will develop. And then I can specify probabilities for the various development possibilities. But I cannot deterministically say how I will get from A to B.
Schrödinger's formula can be used, for example, to calculate where the electron of a hydrogen atom is located and with what probability. This cannot be used to determine the exact position of the electron at any given time, because that is random. Only by random checking will the electron be at a given location with the calculated probability. In quantum physics, it is therefore only possible to specify probabilities for the location of particles.
If we consider a very, very simple atom, a hydrogen atom, the electron can be anywhere and is not anywhere in this cloud at any time. But at any time it can be measured anywhere in this cloud with a certain probability. If we use sufficiently small X-rays, then we can find the electrons somewhere within this cloud. And it is the accepted interpretation of quantum mechanics that this measurement process is indeed random. The electron will be found somewhere in this cloud, and we can calculate with which probability it will be found at which point. But we cannot predict it.
In quantum physics, a particle can be a particle or a wave. You can find out which of the two states the particle is currently in by observing it. In fact, only observation, which is formally a state measurement, forces the particle to assume a specific state. As long as the particle is not observed, it can be in all states simultaneously with different probabilities.
Now, this is something that we can't understand without a blackboard, without mathematics. But it means that two systems that have a common origin are coupled together. For example, you go to a fast food restaurant drive-thru with a friend. You order a Big Mac and a burger, a simple burger. Both are packed in two identical paper bags. The friend gets one, you get the other. We don't know what he's getting. You go your separate ways. You open it. See, you have the Big Mac. Then you know the other person has the burger, even though you haven't spoken to each other on the phone.
The smallest components of our universe are the elementary particles. The particles that are no longer divisible, the fundamental building blocks of matter that make up the microcosm. An intriguing realm of the smallest dimensions.
It's interesting to see how the microcosm is structured. Let's start with a sugar cube. Crystalline sugar. In a crystal, the atoms are arranged very regularly, as you can see here. And if you look closely at an atom, you can see that there's a nucleus in the middle, and the electrons are on the outside, orbiting around it. If you take a closer look at the nucleus, you can see that it's made up of two types of particles, namely the protons, these are the red ones, and the so-called neutrons. They occur in roughly the same ratio. And each of these particles is made up of so-called quarks. You can see them here in green. And that's the lowest level of structure that we know today. There you have it.
Even in ancient times, the great thinkers, natural scientists, and philosophers tried to describe and interpret the order and nature of the cosmos. The four primordial substances form the foundation of our world. The four elements, earth, water, air, and fire. For outer space, philosophers assumed a fifth element with completely different properties, the quintessence. In Aristotle's view of the world, this was an unchanging, eternal substance beyond the sphere of the moon, in which planets and stars move smoothly, also called ether.
So if you start with the four basic elements, it took a relatively long time to realize that the world consists of more than four elements, namely the approximately 100 elements that we have in the periodic table. And to arrange these elements, that is, to determine that they are arranged in the periodic table, was actually only possible when the properties of these pure elements were determined.
The periodic table of elements describes the properties and structure of the building blocks that make up our world, and classifies them accordingly. The result of a process of scientific observation and research. The Russian chemist Dmitry Mendeleev made a significant contribution. In the 1960s, he developed a classification table for the known elements. He sorted them into rows and columns according to their chemical properties and atomic weight. Mendeleev recognized that there is a periodic repetition of properties. He found gaps in his table, space for elements that he was not yet aware of, but which had to exist. These predictions were astonishingly accurate and helped in the discovery of new elements. Over time, the empty spaces were filled.
They said, okay, something's missing here in this periodic table. There should be an element like this. Then they looked for it and found it. Germanium, for example, was discovered in the 19th century.
Other scientists also worked on similar classifications. Then the physicist Henry Moseley classified the elements according to their atomic number instead of their atomic weight, and thus created the form of the periodic table of elements that is generally known and recognized today.
In the 20th century, with quantum theory, it was then possible to explain why the elements are arranged in the periodic table as they are, and not otherwise.
Another pioneer of particle physics was the English researcher John Dalton. In 1803, he presented his own atomic theory, in which the atom is the smallest indivisible unit of matter. According to his idea, there are as many types of atoms as there are chemical elements, each with different masses and sizes, whereby all atoms in a particular element are the same. Different types of atoms can combine to form larger molecules, which determine all the structures in our universe. It took another century to arrive at the standard model of elementary particles that is valid today. The standard model unites all the fundamental building blocks of matter and the forces between them into a coherent system that has withstood all previous doubts, even if we know that it is not yet complete.
According to the standard model of physics, our world works as follows. There are things in the world that interact with each other via so-called fields. For example, the electric field. All fields in our world can be excited, just as you can excite a water surface by tapping on it. And this creates propagating waves. If you excite an electric field, you cause an electromagnetic wave. We also call them light waves. And physics says that waves and particles are related. So light waves consist of particles, so-called photons. For this reason, there are two different types of particles in our world. Firstly, the particles of matter, which are called fermions, and all light particles or interaction particles, which are called bosons. And the great thing is that only recently we have discovered a field, the so-called Higgs field, which interacts with all particles in our world, giving all particles their mass.
The existence of the Higgs field was proven in 2012. With the discovery of the Higgs particle, an excited state of the Higgs field. The proof was obtained at the Giant Particle Accelerator LHC, the Large Hadron Collider, at the European Research Facility CERN in Switzerland. The Big Bang machine, as the researchers also call the ring accelerator, is a giant scientific instrument, the ultimate microscope used by researchers to explore the microcosm, the realm of the most minute particles.
If you want to go to the smallest dimensions, you need the highest energies. And these are things that no longer fit in a small laboratory or on a table, so you have to build exceptionally large instruments, which, because they're so large, are often buried in the ground. These are practically the telescope equivalent of what particle physicists need.
The Higgs particle, also known as the Higgs boson because it is an interacting particle, was the last piece of the puzzle that was still missing in the standard model of elementary particles. With the discovery of the Higgs particle, researchers have come one step closer to understanding our universe. The press likes to call it the God particle. However, it does not owe its name to divine providence, but because it gives all other particles in the universe their mass in a kind of act of creation. In other words, it makes the world what it is. The proof was a decisive breakthrough, but many fundamental questions about our cosmos still remain unanswered.
The fact is that we find things in the universe that we cannot explain with this standard model. The most prominent example is so-called dark matter. This is a matter that we cannot see, but which we know must be there because it apparently forces stars into certain orbits. And this matter must be comprised of some kind of particles. However, it can't be the particles that we know in the standard model. Rather, it must be some other particles that we don't know anything about.
And that is why the standard model cannot yet be the last word, and why researchers are calling for a new machine to shed more light on the subject, an even more powerful and precise particle accelerator. CERN, the European Organization for Nuclear Research, would like to make this wish come true for physicists. It has been planning a new gigantic accelerator for years. The concept includes a 90 to 100 kilometer long circular tunnel. The huge concrete tube is to be built around the city of Geneva, underground in Switzerland and in France. The international project has not yet been approved. However, if the accelerator is built, it would be the world's largest science laboratory with next-generation measuring instruments.
The large instruments are so complex that even individual researchers can't build them. This means that we're working together in large collaborations, so that 3,000 to 6,000 scientists work together on these instruments. So this is not just a physical experiment, it's also a sociological experiment. How do I get 6,000 people from 100 different countries to work together towards one goal?
You can also look deep into the world of the very smallest in northern Germany. At the European XFEL, the abbreviation stands for X-ray free electron laser. The facility, located underground between Hamburg and Schleswig-Holstein, is the most powerful X-ray laser in the world. A linear accelerator accelerates free electrons to almost the speed of light. The facility generates ultra-fast X-ray flashes, 27,000 per second. This makes it a kind of super-fast camera. The researchers use it to create three-dimensional images of molecules, cells, and even viruses.
One of the most important goals of our machine is to make what we call molecular movies. And we need an extremely fast exposure in the X-ray range. So it's like ultra-fast photography, but in the X-ray range with extraordinarily short wavelengths that are small enough to capture atoms. And because atoms are so small, we need an incredible amount of light to be able to image these atoms in an extremely short time. And to generate a lot of light, we need a large machine.
This large machine is a 2-kilometer-long accelerator and a 1-kilometer-long track for generating X-ray light. With the facility and the laboratories connected to it, scientists have the opportunity to look deep into the microcosm. Researchers are also using the X-ray laser to search for our origins. By looking into the tiniest building blocks of biology, they are learning more about how life might have come about. But processes in dimensions at the other end of the scale are also being investigated. Researchers are using the facility to simulate processes within planets.
Here at this facility, we can generate matter in a state like how it exists in the interior of large planets, such as gas giants. And this works with lasers. For example, by focusing very, very intense lasers on a small piece of matter and compressing this matter so intensely that the state that exists in the interior of these large planets is created. The measurement data that we then obtain can be compared to astronomical observations that we make with telescopes. And from this, we can then learn how these planets actually function and how matter behaves when exposed to exceptionally high pressure or extreme temperatures.
Researchers want nothing less than to understand the structure of the world. In the microcosm, they are on the trail of the invisible in order to be able to explain the macrocosm. In the infinite dimensions and complexity of our universe, there are still some unknowns waiting to be discovered.
Exactly 13.8 billion years ago, our universe emerged from the Big Bang, together with space and time. So there was neither space nor time before that. In Einstein's classical field theory of gravitation, our universe emerged from a singularity. And that means nothing else could have existed before that. But today's findings suggest something different. Modern quantum gravity theory says that everything originated from an exceedingly small area of space, which could mean that there could very well have been another universe before ours. Anyway, after the Big Bang, there were only elementary particles, fermions and bosons. After around 380,000 years, they came together to form neutral atoms. And in the process, they emitted energy that can still be seen today as so-called cosmic background radiation.
This baby photo of our universe shows the most accurate map of cosmic background radiation to date. The image is based on data collected by the European Space Telescope Planck from all directions of the compass. The background radiation has slightly different wavelengths in different directions, which is depicted in different colors. This spatial distribution has now been measured by several space telescopes. Using this data, researchers were able to read the curvature of space. In April 2000, they announced their findings for the first time. We live in an absolutely flat universe that will expand for all eternity. The spatial distribution of the background radiation confirms the lightning-like expansion of the universe after the Big Bang, inflation. And it bears witness to when the universe at that time, consisting of a mushy plasma state of quantum particles, transitioned into today's well-formed world of atoms and molecules.
The phenomena of modern quantum physics, for example, play a role at a very simple point in modern cosmology, namely cosmic background radiation. This is thermal radiation that permeates the entire universe. Its spectrum can only be explained if you know quantum physics. In fact, this is how quantum physics began. In 1900, Max Planck was the first to explain thermal radiation with the help of quantum physics. And to explain this cosmic background radiation, you immediately require quantum physics. And there are also small fluctuations in this cosmic background radiation, for example. These fluctuations can only be explained by looking at the smallest particles in the world.
Two physicists, Robert Wilson and Arno Penzias, detected background radiation in 1964. They actually wanted to investigate radio sources in the Milky Way. A faint noise disturbed their measurements. It turned out to be microwave radiation from outer space, part of background radiation. The discovery was a major step in the exploration of our universe, and thus in the search for our origins. The universe in the time shortly after the Big Bang was different from the one we live in today.
In the first brief interval after the Big Bang, which we regard as the beginning of our universe, the universe was very small, very dense, very hot, and it was completely dominated by particle physics. Gravity played no role. Three forces of nature played a role. There's the electromagnetic force that we know. There's the force that holds atomic nuclei together. It's also called the strong force. And there's the force that's responsible for radioactive decay, which is very weak today and can hardly be detected. But back then, in the early days of the universe, when it was simply extremely hot, it played a dominant role and thus helped to determine the fate or the conversation between particles.
Gravity only became important when the universe began to expand and cool down. The era of primordial plasma ended around 380,000 years after the Big Bang. Then atoms and electrons came together to form the first elements.
First, you have this hot plasma, where the homogeneity is the same everywhere, and then condensation nuclei form, where the atoms first condense out and then clump together and attract more and more matter. Because where something already exists, there is the positive force of attraction, the force of gravity, which then attracts more and more, and then the first stars form.
Unlike all other forces, gravity also acts over huge distances. This is why gravity is the dominant force in the microcosm. It forms galaxies and stars, and it is gravity that causes galaxies to merge and stars to collapse at the end of their lifetimes.
What happens to large stars that are at least 3 times as massive as our Sun in the end? It's always the same process. When a star has reached the end of its fusion, it has a gigantic iron core, and then it finally collapses into a neutron star. All the masses fall into this neutron star and then bounce off it. The neutrinos produced in the process promote this rebounding, and so the supernova explosion begins.
The collapse of a massive star means a gigantic explosion. A sudden release of large masses of matter, energy, and light. This explosion is driven by the tiniest and seemingly most insignificant quantum particle we know, the neutrino. But because neutrinos exist in unimaginable numbers, many billions of them pass through our bodies every second. They are what generate the gigantic explosion pressure, and thus cause a star with up to 100 times the mass of our Sun to burst. Neutrinos are difficult to observe. They hardly interact with matter and penetrate even the densest of materials.
All other particles are disturbed in one way or another by what lies between the source of these particles and their detection, perhaps deflected to the left or right by magnetic fields. This does not happen to neutrinos, but the price we pay for this is that they're so difficult to detect.
Simulations of supernova explosions are based on complex physical models. Both gravity and the interactions of particles at the subatomic level must be taken into account. And so these huge explosions in the macro world of the universe can only be understood by delving deep into the world of the smallest, the world of quantum physics.
There are many things in the larger world that you couldn't understand without quantum physics, without the exceedingly small things. For example, you can only understand why an atom is stable if you look into the quantum world, if you understand quantum mechanics. There are many things in the macro world that you can't understand without knowing how it works on a small scale, and how the individual atom works.
Supernova explosions are characterized by a sudden flash of light in the universe. For a short time, they are so bright that they can outshine entire galaxies. Researchers can see the remnants of such cosmic events. For example, at the Crab Nebula, which is more than 6,000 light-years away. It glows in different colors due to the ionized gases left over from the explosion. Each color is a characteristic fingerprint for the respective chemical element that was hurled into space. These include oxygen, carbon, nitrogen, and silicates, which were incubated inside such stars. The building blocks from which the Earth and ultimately we humans were formed were created in such supernova explosions. Humans are made of stardust. Their existence is closely linked to the Big Bang and the dying stars in the further development of our cosmos. The universe continues to expand into infinity. This means that the distances between the galaxies are increasing, while space itself is expanding.
What actually is space? For a long time, physicists believed that it was a kind of stage on which everything happens. But we know better today. Space is a kind of container with an internal structure that gives it certain properties. We have the Higgs field, for example, but there are also what we call virtual particles. What are they? Virtual particles are pairs of particles that are created ad hoc somewhere and decay again in a very short time. They don't really exist, but only virtually. And these virtual particles make it possible for a light source to travel through the vacuum. In the same way, they expand the universe in such a way that it's spreading out faster and faster. And according to a new theory, all virtual particles might even be entangled with each other. And this entanglement, together with the virtual particles, creates space.
The idea that pairs of virtual particles are constantly forming everywhere in the vacuum of space comes from theoretical physics and quantum mechanics, or rather, quantum field theory. Entangled means that the particles are coupled in such a way that the state of one particle immediately influences the state of the other, regardless of the distance between them.
An essential element that contributes to quantum theory's lack of intuitiveness is entanglement. Entanglement means that states are coupled together. If, for example, you create two particles at the same time, and these particles move away from each other, that is, two microscopic particles, then according to quantum theory, they remain mysteriously linked to each other. As long as you don't carry out a measurement. If you now carry out a measurement on one particle, the other particle will automatically show a result. In other words, they are somehow linked. And the completely mysterious thing is that quantum theory tells us that as long as no measurement occurs, they remain coupled over any given distance. And if somebody has an idea how they're linked together, please let me know.
Virtual particles are not yet directly observable. However, they do have measurable effects in the macrocosm. For example, events can occur in the vicinity of black holes in which virtual particles could play a significant role. Black holes are gravitational monsters that devour everything in their vicinity. Black holes are formed at the end of the life cycle of massive stars. When such a star has exhausted its fuel reserves, it can no longer generate the necessary energy to counteract the force of gravity. Even neutrons can no longer withstand the enormous gravitational pressure. The star collapses into a black hole, an incredible accumulation of mass in a tiny space. According to Albert Einstein's theory of relativity, nothing that comes too close to it can escape a black hole. Even light is swallowed up. That is why a black hole is black. In their vicinity, however, quantum mechanical effects play a role.
There's a lot of energy in a black hole, and energy can always change into a particle and an antiparticle for a short time. Let's imagine that this quantum fluctuation happens exactly at the horizon and that energy is converted into a particle and an antiparticle at the horizon. The particle is on the good side of the horizon. The antiparticle is on the bad side of the horizon. So one is sucked in by the black hole, the other escapes. In this way, radiation could escape. The black hole loses energy, because every particle that escapes corresponds to energy. And if this process happens often enough, the black hole shrinks and becomes smaller and smaller until it eventually disappears.
It was the physicist Stephen Hawking who developed this concept. According to Einstein's general theory of relativity, a black hole would pull everything, including light, into itself. Nothing can escape. According to Hawking, however, real pairs could spontaneously arise from the virtual particle pairs of the vacuum at the event horizon of a black hole, which are then separated, with one of them falling into the black hole, thereby melting its mass, while the other escapes into the depths of the universe. The Hawking radiation, named after the physicist. The theory is a step on the way to solving one of the greatest mysteries of physics. Researchers are looking for a way to unite the fundamental principles of the macrocosm with those of the microcosm, and thus to apply quantum mechanics to places of extreme gravity, which are described by Einstein's theory of relativity. Researchers are searching for a unified theory, quantum gravity, one formula for everything.
The structures of both theories are such that they don't fit together at all. And that's the challenge. If you manage to combine these two theories into one large superstructure, then you'll have the world formula. And nature actually shows us that it must exist. But we haven't found it yet.
Researchers have a clear idea of how to get from the time shortly after the Big Bang to today's universe. However, both the world on a small scale and the world on a large scale still pose many mysteries. For example, how we get from the laws of physics to living nature is completely unclear.
We know how molecules can be formed, but we don't know exactly how the selection of molecules comes about. We don't know why our DNA is left-handed and not right-handed, which has led to this asymmetry in the spiral direction of our DNA. So no formula can help us at the moment. Is this the case everywhere? Are there perhaps planets elsewhere where this is not the case? Is it perhaps something random? Or is it physics that says it has to be left-handed everywhere?
The microcosm is also responsible for generating energy in the universe. The fusion of the hydrogen nuclei in the center of a star generates the star's energy, and the sun radiates photons into the universe as light. They also illuminate and heat the Earth. Whether all of this, the microcosm connected with the macrocosm, can be described in a comprehensive formula, a world formula, is written in the stars.
Will we find the world formula at some point? Yes, we might, but it's not important. It won't do us any good. Why? It will never be able to calculate chance. Of course, that would be very useful, for example, to predict tomorrow's lottery numbers. Besides, to calculate the future, you need to know the exact state today. In other words, the position of all the atoms in the entire universe. Of course, that's practically impossible. Let's look at the microcosm one more time. It determines both the Big Bang and the end of our universe. For the latter, there are two possibilities. Either all particles in the universe will go into a state of maximum disorder. This is called thermal death or the Big Freeze. Or the second possibility, the virtual particles will cause space to expand so much that everything will be torn apart down to the last atom. One prospect is as unpleasant as the other. But there's no need to worry. According to the latest data, this big freeze will not occur for another 500 billion years.
If we want to understand the universe as a macrocosm, we must also understand the smallest particles, the microcosm. This is a key finding of modern cosmology. However, infinity is just as difficult for the human mind to grasp as the smallest building blocks that make up the elementary particles. Macrocosm and microcosm. The world on a large scale and the world on a small scale are vastly different. Together, they determine the beginning and the end of our existence. And it may well be that in the infinity of our universe, a new physics awaits researchers that is not yet within their reach.